Okay, so here we go. So I'm just going to give you a couple of notes here. And this is good stuff. And that's why we're learning it at the beginning, because everything we're going to do the rest of the year is connected to this. So what we're doing is we looked at trends, and we're trying to figure out why atoms act the way they do. Okay? So we're looking at atomic structure and electron configuration today. So this is topic 1.5. This is standard 1.5, and this is what you're going to have your quiz on next time, okay? Dig out my notes. So we start with all these rules. So we have 3 rules that we have to follow when we do electron configurations. The first rule is from Wolfgang Pauli. It's called Pauli exclusion principle. And you probably already have this written down, so just go to where you had it written down and add what I'm going to add to it. Okay? You're adding to your notes in the margin. Pauli says that you can add not only 2 electrons to the same orbital. So 2 electrons per orbital. This is if you have your box, you can only have 2 arrows in it. That's all that means. So every box can only have 2 arrows. So that's our first rule. The second rule is Hund's rule. And Hund's rule means you have to hand your electrons out evenly. And the electrons out evenly. They were much more scientific. I equated it to handing cards out. When I have taught it to you, they are putting electrons in energy levels. So the orbitals actually have energy themselves. And what they did is they said, hey, this orbital has this much energy, this orbital has this much energy, and we're going to put the electrons here because of how much energy they have. And that's what they're talking about right here. So the increase in energy as they go away from the nucleus. Okay? The increase in energy as you go away from the nucleus. So this is how you fill them. Alright? So this right here, notice there's 3 orbitals. We're going to put 1 electron in each orbital and then go back and put electrons in the other ones. Okay? That's what Hund's rule says. Okay? And what's the last rule? So let's say we have 2p. I have 3 orbitals. I'm going to put an electron in each orbital. Right? That's Hund's rule. What's the last one? There's Pauli exclusion principle, Hund's law, and what's the other one? Do you remember? Hund's rule.
Quantum theory?
No, the quantum theory is what we're doing. This whole big kit and caboodle is quantum theory. What was the last one? find it. There's one more. And it just slipped my mind.
Off the do principle?
Yeah, the off-blue principle. Thank you. And I spelled it wrong. What does that say, Luke? That says one electron is going to be spinning to the right, the other electron is going to be spinning to the left. So this says that your arrows are going to go opposite directions. The spins of the electrons in the orbital are opposite. Thank you, Luke. You saved me. I just saw someone blank. Okay. So, those are our 3 rules that we need to follow. Now, with our rules, we have all these new symbols. Okay? So, each symbol is a different level of organization. Okay? And that's what we're doing, is we're keeping track of our electrons, because the more electrons they have, the different chemical properties that they're going to have, and it also affects the trends on the periodic table, and it affects the size of the atom. Okay? Because it also, where these electrons are, affects the Coulombic force. Okay? And some of these atoms build up shields. In the atom, there's a shield. And there's this thing called shielding effect. Do you remember reading about that? Okay, and that has to do with the effective nuclear charge, which they did a great job of defining, and I'll define quickly today. And the effective nuclear charge is directly related to which trend? Atomic
Gravity.
radius, not gravity. Okay. Okay, so now I'm going to go through all the new symbols. Okay, so our first new symbol that we learned about, and it shouldn't have been new, is a little n. Little n is energy level. Now, energy level has several different names. You could call it principal, energy level. You could call it energy level. You could call it a quantum number. I think they called it something even beyond that. What else did they call it? They called it an electron shell. I tried to write them all down in my notes. Okay? They called it a principal, also a principal quantum number. Look at all those names for n. That's crazy, isn't it? No wonder it's confusing. All it is the energy levels. And the energy levels are on your periodic table. Do you remember how you figured out the energy level of an element? The energy level is the row, or the period. So that's the energy level. So barium, how many energy levels does it have? Barium has 1, 2, 3, 4, 5, 6. So it's going to have 6 circles around it. And we're going to have to put those electrons in the circles. Okay? So that's why there's a 6 right there. Okay? Scandium, how many energy levels does that have? 1, 2, 3, 4. So you count to see what period it is. Alright? Now, if you take AP Bio, Mr. Robson has you draw circles. Let's say, here's the nucleus. He's drawing the circles. The circles are the energy levels. Okay? The number of circles that something has is the period that it is in. So the number of circles is equivalent to the period on the periodic table. So this one right here has 1, 2, 3. So it must be automatically, I'm looking at these elements right here, and that's it. I just narrowed it down to all the elements in the third period. It's not going to be the ones before that. It's not going to be the ones after it. If n equals 3, those are the elements we're looking at. Okay? Yes?
So when you go on to like the next element for the next row, all of a sudden this new circle just appears.
It does. And let's connect that to our energy, right? Because that element now, or that electron, has energy, right?
Mm-hmm.
Yeah. So you're going to add another line of energy right here. So do you see how they went from this right here to this right here? They actually developed this from this. Okay? And this explains why all of a sudden it goes from 4s to 3d. Because 3d is actually between 4s and 3p and 4p. So 4s would actually be right here, and 4p would be right there on that energy chart. Okay? Does that make sense? All right? Okay. So, n can only be what numbers? How many numbers can there be for n? Only 7. So n can either be a 1, a 2, a 3, a 4, a 5, a 6, or a 7. It's never going to be a 0. It's never going to be a negative number. Never ever. If you see a 0 or a negative number, that option is false. That is not an option on a multiple choice test. Okay? So are you good with n's?
Yeah.
Okay, good. Now, inside these lines, we have what?
S.
We have sublevels. One of the sublevels is S. Another option is P. Another one is D. And another one is F. Okay? So, inside N, there are...
Mom? How come on the top of this graph it says n equals 8?
N equals 8. Where does it say that?
On the page
N equals 8. I do not see N equals 8. Oh, because I can excite the electrons in 7 and get them to go to 8. 8 is fleeting. Good point. There are sublevels. So our sublevels that we learned are S, P, D, and F, right? There's 3 types. So now we have a symbol for a sublevel. Our symbol for this is a lowercase l. So every time you're looking at an L, every time there's an L, what do you automatically shift to in your brain?
Electron configuration.
No. You shift to, I wonder if it's an S, I wonder if it's a P, I wonder if it's a D, I wonder if it's an F. It's going to be one of those. The crazy thing is, they made on L, you have to start counting at 0. So to figure out what L is, you have to take n minus 1. So L can never be equal to n. Alright? Write that down. L can never be equal to n. It's always going to be 1 less than it. Now, What does L tell you? It tells you whether it's an S, a P, a D, and an F. So it tells you the shape of the orbital. Okay? So S would be what? 0. P would be what? 1. D would be what? 2. And F would be what? 3. Right? Those would be the value of L for those shapes. That make sense? Okay. Now I'm going to go to the hard one. I'm going to go to this guy. M sub L. M sub L is the orbital. And there's a lot of them. This is where you can have like a long list, like they do on page, where's that at? Right here. Look at all the L's. So there's N, this is L. Look at all the possible L's I could have here. See that?
What page are you on?
I'm on page 251. Look at all the possible orbitals I could have there. Okay? So, how do you figure out what L is? First of all, let's tell you what L is called. There's a name for M sub L, and that is called the magnetic quantum number. And what it is, it's the number of orbitals in that sublevel. Okay? And we learned that. How many orbitals are in S? How many lines or boxes do you draw for an S? You draw one box. How many? So that's an orbital. So your M sub L here would be what? How many boxes did you draw?
1.
Well, how many boxes did I draw?
1 for S.
1. M sub L would be 1 for S. Okay? How many boxes did I draw for P? 3. What would my M sub L be for P? 3. No. It's the number of boxes. The number of orbitals. You're putting the electrons in the orbital. I want you to count how many boxes there are. So the M sub L for S would be 1. For P, it's 3. Okay? For D, how many boxes do you draw for D?
6.
5. 1, 2, 3, 4, 5. You draw 3 lines for D, or 5 lines for D. How many pictures are there? Right? We're counting how many pictures there are. Each picture is a box. Okay? So P has 3 boxes, right? How many boxes does D have? 5 pictures. Because it holds 10 electrons. Right? So ML there would be what? 5 for D. Okay? What about F? How many boxes do you draw for F?
7.
7. now let's go back to our book. Look. Now you should understand where these 1, 3, 5, and 7 come from. You see that? The 7 is the F. Do you see that? Does that make sense to you? You already know this. You just didn't know the what part?
Variable.
The variable part. You just didn't know what was called ML. Does that make sense? Are you with me? Yeah, kind of. What are you confused on?
I'm confused what that chart's supposed to show. Like,
Well, don't worry about that. Do you understand this column right here?
like what?
Do you understand where I got the 1, 3, 5, and 7?
Yeah,
Okay, that's good. Do you understand why the 7 matches with the F?
because there's 7 orbitals in the F.
Correct. Okay. So, now, the next level is now we're going to start putting electrons in here. And we use arrows for the electrons, right? The symbol for our electrons is M sub s. This is called our magnetic spin, right? The electron spin quantum number. And it could either spin one way. It could either be a plus 1/2 or a minus 1/2. So that would be my up arrow and that would be my down arrow. Okay, now let's say you wanted to figure out the total number of electrons in one energy level. There's actual equation for that. So if you wanted to figure out the number of electrons in one energy level of your choice, here's what you need to do. You need to take 2 and n squared. Now where's the n? What is n?
The energy level.
Yes. So you should that should be helpful. Okay? Now we need to talk about sub ML. ML gets really, really complicated. Okay? You use L to calculate ML. So we're going to write a mathematical equation for ML. You ready? So the number of orbitals can be determined by L. So let's say if we have L equals 2. How do I know what all the possible MLs are? Because there's more than one. The answer is if L is 2, ML is going to be -2, -1, 0, 1, or 2. Is that crazy?
Wait, what?
How do you feel about that?
How'd you get those numbers?
Well, the rule that I'm trying to say is if you want all the possible MLs, what you're going to do is take the L, put a negative in front of it, and write down all the numbers, including 0, until you get to that positive number.
Well,
So
why
How do you know
start
what
at
to use?
-2?
What?
Why do you start at -2 to get to 2?
Because that's the formula we're using. That's the formula that you use for ML.
So you always start at -2.
You always going to start at the negative of whatever the L is. So if I gave you L1, what would you write?
Negative 1, 0, 1.
Okay? And this has to do with the orientation of the electrons in space. Okay? Alright. So that was hard. Now, that's where these things come from right here. So you should understand if we're looking at 1s, the n is a 1, the L is a 0. Do you understand why that's a 0? How do you find L? N minus what? 1. And if n is a 1, 1 minus 1 is what?
0.
0. So that's where they get the 0 for the L. And now, how do we know what ML is? Right. Yes.
N is the energy level then?
And it's the energy level.
Okay, so yeah.
Okay? So ML is going to be a little cloudy to you. If you don't totally understand ML, that's okay. But you should definitely understand this one. The spin. If the arrow's going down, it's going to be a minus. If it's going up, it's going to be a plus. Okay?
You always put the up arrow first, I forget.
It doesn't matter if you put them first or as long as they're going opposite directions, they're fine. Doesn't matter which one's first.
So it's the number of boxes?
Huh?
And it's the number of boxes?
N?
It's the number of
No.
energy.
N is this number right here.
No, okay.
So that means that's in the first period.
Correct.
So like if it's, well if there's like a 2p, would that be 2?
Well, let's do that. Let's do our homework now. Let's look at our homework problems. Oh, before we look at our homework problems, there's one thing I need to say. Gotta make sure we get the definition for effective nuclear charge down. Make sure you find this definition. You probably already have it. I want to make sure you understand it. It's the net charge experienced by the electron in a multi-electron atom. So in an atom that has many electrons, you're just looking at one of it. And it's a balance between the attractive force, because remember that the electron's negative and the nucleus is positive, so the electron's going to be attracted to the nucleus, right? So it's a balance between the attractive force and the force of repulsion. Now what would that electron be repulsed by?
Proton?
Positive.
Electrons like protons.
Oh,
So another electron.
Another electron. So that's what effective nuclear charge is. It's the balance between the repulsive force and the attractive force. Okay? That determines the size of the atom. Because sometimes they have so many electrons that there's a shield. So the elements that are small, there is no shield here. That attractive force is winning. The elements that are large, like cesium and barium, that have a large atomic radius, there's a shield there. And that effective nuclear charge is decreased. There's so many electrons that are close to the nucleus that electron out here isn't attracted to the nucleus anymore. Because there's a shield of electrons already doing that. And it pulls them in, and then they get really close. And so now we have a whole bunch of electrons that are really close. So is that electron going to sense the positivity here? No, it's going to sense that really thick negative shield of electrons. And then that is going to be bigger. That's called the shielding effect. And that's what makes our atomic trend, our radius trend, the way it is. Does that make sense? Okay, so I'm done talking about that. Now let's go to your homework. Mine is kind of messy, and I too hated drawing the boxes. This is what I have for number 1.
So we don't need, oh, we do need to draw the boxes.
Okay, I drew lines instead of boxes.
So what's the reason for not doing 2 in 1 and then 1 and then leaving the other blank? But doing
Okay, remember we said 3 rules. One rule is I have to have 2 arrows per orbital, right? The second rule is I hand my electrons out evenly. So I'm going to put an arrow here, an arrow here, and an arrow there.
Oh,
And I have 4, so then I'm going to go back and put that one there. Okay? Now what does this say? This one right here, if it wants to be stable, it's missing an electron right there. So a light should be going off in your head and saying, hey, what's this going to do? It's either going to become an ion, or it's going to go through a chemical reaction. Because it's missing that electron right there.
Wait, say that again?
Notice it's missing this electron right here. Do you see that? It only has 7. And we learned last year that this right here is what causes it to become an ion. This is going to become an anion. It's going to go out and get an electron, put it there, and now it's going to go from being 17 to being having 18 electrons. The number of protons stays the same, so it's still chlorine. And now it's become chloride. Remember working on that?
Yeah. What about phosphorus?
Phosphorus is missing 3. So that's going to become P3 minus. Phosphide.
Is there phosphorus with the 3?
Yes, there's elemental phosphorus. And it comes in 3 colors. Red, white, and yellow. Phosphorus is very, very unstable.
I feel like every element's unstable.
No, phosphorus is very bad. You don't know when it's going to explode. And when it does explode, it keeps on burning whatever it touched. So if I had it in my hand and it exploded, over here to the tile, it would burn a hole through the tile, burn a hole through the cement. They used to put phosphorus at the end of their ammunition in the Revolutionary War. So that when you got hit by a slug, if you didn't dig it out, it would keep burning a hole in your body. It was the first chemical warfare. Yes.
How did you get to like, how you have like the phosphorus and the chlorine? How did you get the 1s, 2s?
Okay.
Where did you get those?
I followed my zigzag pattern.
So,
Remember our zigzag
so
pattern?
are we gonna have to memorize that?
You should be able to see it on the periodic table.
Because if it's
It's right here. Remember? S. These are all S's.
wait, what's all this is?
Group 1 and group 2. We're always filling the S's.
So the
Except for
S's,
helium and hydrogen.
so those S's will always be full.
Not always. Magnesium. Yeah. Lithium isn't going to have a full S.
Why?
Well, let's do it. Lithium is how many electrons?
3.
3. So what do I start with?
1s.
And S's hold what?
2.
Then I go to what?
2s. 2.
No? I have to add these numbers to what?
3. 1.
Yeah.
Oh,
My
'cause you only
exponents
need
have to
two.
add up to equal that, remember?
So then you just draw the first box with 2 arrows, the other one's just 1.
And I should put 1s, 2, and 2s1 back under.
So pretty much.
Do you understand why?
Yeah, I just have a hard time remembering where the 1s, the 2s, the 2p, like, how do you know when you're going to get to a P?
Okay, these are the S's.
Okay.
These are the P's. This is the P block.
So nothing over
P1,
group 1 and 2 will have a P in it?
never.
And we just have to know that?
Yeah, because that's the S block. This is 1P, 2P, 3P, 4P, 5P, 6P. Right?
And then after that, it just repeats.
Then it goes to D's. Okay? This is 3D.
And each D can only hold
10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Does that make sense? So you don't even have to remember the numbers. All you have to do is be able to read the periodic table. And look, it goes 1s, 2s, 2p, 3s, 3p, 4s, and there's one you gotta remember, 3d, and then 4p. You just keep on going.
So how come after you get, so if you get 2 S's and a P and then you go back to S?
Yeah. Why do we do that? Because of how much energy they have. 1s has this much energy. 2s has this much energy. And we're
So
putting them in order based on how much energy they have. Okay? Does that make sense?
I think so.
Okay. So you shouldn't need to do the exact pattern anymore.
True.
I'm not brilliant. I can do electron configuration just by glancing at the periodic table. Everybody thought I was brilliant last year in chemistry because I could rattle it off. All I'm doing is reading the periodic table and counting boxes. 2, 10, 6, 6, and then how many down here?
16.
14.
Whoa.
Okay?
So can you show me chlorine?
Chlorine's right here.
How you did that one?
Sure.
That's one of the favorites.
Chlorine. So do you see how I did it right here? This is a P.
So is 1s hydrogen?
1s1. Yes. 1s2 is helium. 1s2, 2s1 is lithium. 1s2, 2s2 is beryllium. 1s2, 2s2, 2p1 is boron.
Whoa. That's crazy. I never really put 2 and 2 together.
Yes. Luke, how are you feeling about this?
Okay.
Okay? Alright. Now, number 2. For some reason I skipped number 2. I'll do it. What do we have to do? We have to use SPF notation. So let me show you how I would do magnesium. So I'm going to start with 1. We always start with 1s. Then we fill it. Then we go to 2s. We fill it. 2p6. And then I have 3s2. And then these numbers have to add up to equal 12. Argon. And then we have the octet rule. Remember, we add the 2 and the 6 together and we get 8. And everything's trying to get to 8. Alright. And I should draw the box, the diagrams. I have 1 box for S's. How many boxes for P's?
3.
3.
So since the P column is 6 elements wide, that's why you need 3 boxes so 6 electrons can fit in there.
Correct. That's what I've been trying to explain to you. You get it. Okay? And each one of these, so if you wanted to be sassy, you could do your ML. Okay? How many, what would your ML for 18 be?
So you take L equals 18?
Well, how do we get L?
L is going to be 2 because we're in the third energy level. And 3 minus 1 is 2.
Okay. So then,
And so then ML is going to be -2,
So-
1, 0, 1, 2.
you're using, and Luke just used, okay, so what, let's do that quick, if you're being curious. Well, we did it, well, let's do it in number 11. Number 11 was a hard one. 11A, it says, what is the maximum number of electrons that can be identified with each of the following sets of quantum numbers? Okay, so the answer for A is 2. Why is my answer here 2?
Because you take the N.
So we're in the 4th energy level. What sublevel are we in?
Third.
What is the 3rd sublevel? L equals what? 3.
3. Wait, that's the third. Oh, yeah.
Okay, these are our L's. If L equals 3, which one of these are we in?
F.
F, so we have a lot of L's. So then my L would be -3, -2, -1, 0,
And it goes up to 3.
1, 2, 3. We have a 3 there.
But then why did you write ML1?
Okay. Of those L's, those are our MLs. I have a lot to pick. Now I picked one of them.
Why?
Well, that's just the problem that they picked.
They want you to pick one?
They picked one.
Oh,
They said of those that we listed, we're looking at one. How many possible electrons can you have in that orbital?
2.
2. That's why I got 2.
So if it was if ML equals 2, then you could have put the answer would have been 4.
No.
Because
I can only hold 2 electrons in one orbital. And this says, hey, we're looking at the 1 orbital.
Okay, but if we had 2 orbitals, the answer
There
would
won't
be
be
4.
2 because they just listed one ML. If they wanted 2, then they would have had to write ML, comma, negative or 2. Then they're listing both MLs. ML is an orbital.
Yeah.
ML is one of these. They only want this one. They don't want 2.
If they want to, would it have been?
They won't.
Oh.
So they
They won't
never
do
want
that.
to? Okay.
They're not going to do that. Okay, then B. It says, okay, now we're in the 6th energy level, the 6th period. So think about the elements that are in the 6th period. There's a lot of them. We're looking at L1.
So first.
Remember, you can have any number under 5. So 6 minus 1 is 5. So it could have been 0, 1, 2, 3, 4, 5. So we're still in the top line. And look at, I listed all the possible MLs. Do you see them all? Look at them all. That's a lot. Because I can go from whatever the L is, and it's a 5. Or
Where are
actually,
you getting -6 from?
I don't know. Sorry. It's -5. And then I'm picking this one.
Wait, again, so how did you get the -5? You took the N
I-
minus ML?
I took N minus 1.
Because that's the L.
That's the L.
So you take N minus L and that gets you your M.
No. N minus 1 is equal to L. Right?
But so you take N minus L?
No, I never did that.
Because that's what.
What did we write down? How did we figure out L? L is equal to N
It's
minus
always
1. That's it. So I wanted to find L. So what did I do? I took the N minus 1. So L is, it can only go to 5. And it starts at 0. Okay? So I can have, for all my possible L's, I have 0, 1, 2, 3, 4, 5. However, how do I get ML? Whatever my possible highest L is, I take the negative of that. Remember? So my possible highest L is 5. Right? We're looking at 1. How do I find all my MLs? I go from negative L all the way to positive L. So that's where I get from the negative 5 to 5. So now the ML that we're looking at is this one. We're just looking at that one. And then there's an electron that's spinning counterclockwise. So how many electrons are there?
Wait, what? How did they find the MS?
Okay, they just wrote the problem in the book.
Oh, so that's just what it is?
Yeah, if you read the problem, that's what they're saying. Here's the electron we're looking at. How many possible electrons could that be? They're just checking your understanding to see, do you understand what these things mean?
A little. Like, yeah, but.
So do you understand why the answer is 1? Because I'm looking at exactly 1 electron. I'm looking at an electron in period 6, L1, and of all the MLs, I'm looking at this one, and the electron in that orbital is spinning counterclockwise.
Yep.
That's what this says. So it's kind of like a website name. It's like telling you, it's like an address. Okay, here's the house number. Here's your street. Here's your city. And here's your country. Okay? Alright, now C. C is tricky. Here they're looking to see if you know how to do this. They're just scaring you with these letters. That's all they're doing. Don't let them do it. Here, you're like, oh, I'm in the 3rd energy level. Can I have an L that is equivalent to N?
No.
No, this is instantly wrong. So the answer is none. Because L is not equal to N, ever. Do you see how they are just trying to get you to follow the rules? Okay, so that was the hard one of the bunch. Then we go back to normal stuff. Here's 15. Gallium. Are you good with the electron configuration? Then I did the noble gas configurations, because noble, notice, everything here is completely full.
Oh, now
So then I use my shortcut.
Yeah.
Wait, what?
These are all full.
Yeah.
So we can cut it off right here. And what's this, the electron configuration for right here?
Argon.
Argon. So I can put argon in brackets.
Oh my.
Wait.
That's so.
Me and Drew figured that out last year.
Yes, you did.
That when everything's full, it's just argon and then.
No, remember you have to go to the noble gas before it. So we're in gallium.
Yeah.
Go to the noble gas before it. So you go back. The noble gas before it is argon.
Okay.
So then you put argon in brackets, and you take off, you take 18 from the 31. 31 minus minus 18. And that is how many electrons I need to place. So
Where do you
I start here.
So you just know where to start.
I start with the energy level that the element's in. So it's in the 4th energy level. And I start with 4s, always. So whatever energy level it's in, I always start with the s of that.
Oh.
Okay? So then I have 4s2, 3d10,
This is crazy.
4p1. Okay?
Sure.
Alright. So that's good. Let's not worry about the quantum number stuff there. Let's go on to your next problem, which is 17. 17 is very important. So this is a definite AP test question. Here are your forming ions. I want you to think about why would these be this way?
Because you want one arrow left in the box.
You don't want an arrow left by itself in the box.
Yeah, you do, because you're making 9.
Well, for
No.
energy 2 plus, you want 2 less, so you just do magnesium without 2 electrons.
Correct.
Wait.
So you would do magnesium,
Yeah.
that has, it would end up with 3s2. If you did magnesium
You
normally,
just take that out.
you're going to take the 3s2 out, and then you have magnesium ion. Right?
Oh, now I see.
Then you have potassium. Potassium would normally be 4s1. Now we need to get rid of that 1. Either needs to go to 8, or you could throw it out.
You're going to 8.
Going to the 8 is going to take a lot of energy.
But that's what you did.
No, I didn't. I don't have 4s1 there. I threw it out. I let the electron go into solution. We're going to do something else with it later. Okay? Chloride is the opposite. Instead of throwing electrons out, what's it going to do?
It's gonna
Take
do-
it in.
It's going to go and get it. And it's going to fill that last p orbital. So it's going to go from being 3p5 to a 3p6. And that's where it gets its negative charge, because now it has more electrons and protons. Oxide is going to do the same thing. That's going to go from being 2p4 to 2p6. Yes.
So when you look at that and you quick see how many like P whatever, since it's the 5th one in the row, so it's P5.
Yes.
And then like if it's down there, would it be like
Where? Down here.
like zinc? Would that be like D10?
10. So this is D9, D8, D6,
So
D7. Yeah. That's why the periodic table is so brilliant.
it's crazy how everything's like.
Yeah, that's what I was thinking.
That's like should be one of the 7 wonders of the world.
Well, think of the guy that put this together. He had no idea that electron configurations even existed.
So he's like, oh, it just like worked out.
It did.
Is it like,
Yeah.
that's so weird.
And it is the basis of everything, which is why we started with it. So now, after this, we have to start thinking about why does nitrogen all bond with oxygen? And when it does bond with oxygen, it's going to bond with oxygen in a certain way and a certain shape. And the way it bonds and the shape that it has will also determine its chemical and physical properties.
So for number 17 on chlorine,
Yes.
why do you have a 6 and how come it all adds up to be 18 instead of 17? Is that because the 1 minus after the chlorine?
Yes. Okay, so normal chlorine is this, right? That's normal chlorine. Do you see how this is not a 6 right here?
Yeah.
Chlorine is a halogen. It is definitely an elemental form, right? We learned that. Why is it deadly?
Because it's missing.
And it's going to rip an electron off of anything it comes in contact with. Okay? It'll tear it apart. This already has an electron.
And that's more stable.
And this is more stable, and you eat this.
And he's happy.
It's happy. It's in your body, floating around. Okay? Alright. Okay. Here, now we're adding another layer. Sorry, my brown came through. Paramagnetic and diamagnetic. So now you're understanding why something has a magnetic field. Okay? So there's two types, para and di. Para means that, do you see how these orbitals are full? Oh, I'm sorry. Para means that this orbital is not full. Anytime you have an orbital that's not full and it's in the d, it's going to be paramagnetic. Anytime you have an orbital that's full and it's in the d, well, actually, yeah, it's in the d. It became an ion. Titanium's, you understand that titanium's in the d, but it's not in the d because it gave the two electrons away, right?
Oh, yeah.
Okay. It gave the electrons away. Now it's stable, so that's diamagnetic. So that's an easy way to remember those two. The word shouldn't scare you. Para means, hey, there's not a friend there. It's unstable. Diamagnetic means everything's happy. Okay?
Yeah.
So those are your two types of magnetism.
So are the alkaline earth metals all mass? Like even
Yes.
Fr and Ra?
Yes. Did you just have a major aha moment?
What?
Did you just have a major aha moment? That's good.
Announcements.
Okay, so we're done for the day. You're going to have a quiz on this next time. Okay? I'm not going to assign anything else because I want you to study this and understand it really well. You might have to reread the section. And if you come up with a question, you can always email me and we could do a Google Meet or something. Alright? Yes. You don't have to raise your hand. There's only 3 people in the class. I'm going to stop my video though.